So our next talk is a dual talk by both people from Nvidia and Netflix. So Amr and Ryan will be from Nvidia will be talking about the Triton inference server, and then Lipping and Fan from Netflix will be talking how we use it in our model scoring service. Thank you.
Hello, everybody. My name is Amr Elmeleegy. I'm with the product marketing team at Nvidia. Very excited to be here today to talk to you about the Nvidia Triton inference server, which is one of multiple open source applications, SDKs, and libraries that Nvidia makes available to the user community to help accelerate time to market for putting AI models into production. I'm also going to be joined in a few minutes here with my colleague, Ryan McCormick from our Triton engineering team to cover some of the more technical aspects of the product. Now, we have a short time here today together. We put together a fairly simple agenda. We're going to start talking a little bit about some of the common challenges that we see as enterprises are trying to put some AI models into production. And then talk a little bit or zoom out and talk about the end-to-end inference stack from NVIDIA and how that full stack helps solve some particular challenges with AI inferencing. And then we're going to zoom back into the NVIDIA Triton inference server so you can get a bit of a visual understanding of where it sits in that AI inferencing stack and talk a little bit about some of the capabilities there, deep dive into the architecture. And then finally, we're going to just wrap up with some hopefully helpful links of where you can get started and go ahead and download the product and maybe even use it in a launchpad setting for experimentation purposes. Now, I have a little bit of a confession to make. I just recently joined NVIDIA. I'm only a few months in. And prior to joining NVIDIA, I actually knew, of course, that NVIDIA had a lot of open source applications and SDKs for the community. I just was not aware of how widely adopted these solutions are in the market. Now, this is just a very simple slide that talks a little bit about some of the enterprises that are using the product out there. You can clearly see some big brand names, but we're also equally proud about some of the smaller, medium-sized enterprises that are using the product in production, and particularly as well some of the startups that are using the product in production. And the reason for that is it speaks a little bit about the simplicity and ease of use of NVIDIA's open source AI inferencing solutions. It doesn't require an army of IT developers. It doesn't require sophisticated machine learning engineers and advanced machine learning engineers to deploy it. We've got examples, and I'm just going to call one example here. Wealthsimple is a fintech company based out of Canada. The entire company has 600 employees, and they've been able to use the NVIDIA inference platform to help accelerate and reduce time to market of putting AI models into production from literally 3 months down to 15 minutes. And that's a very, very small team of IT and machine learning engineers and IT staff that was able to use the product and help get value out of it. Now, of course, throughout these experiences working with some of these enterprises across different industries, we started seeing some very common challenges when it comes to deploying AI inferencing into production. Now, myself, I come from, prior to joining NVIDIA, I've worked in the enterprise resource planning space for quite a bit of time. And I can tell by just looking at a high level of these challenges, none of these at the surface can look very specific to AI inferencing. Every application needs to be fast. Every application needs to be interoperable. Every enterprise application has to integrate within the existing ecosystem. But as you start peeling the onion a little bit and looking a bit deeper underneath these aspects, you're going to start seeing some very intricate challenges that are particularly unique to AI inferencing that require some particular capabilities in order to address. So for example, when you talk about latency and speed, a lot of enterprises today are deploying not just a single model into production, they're deploying hundreds of models into productions. And a lot of these models are serving very different applications that can have very different service level agreements. Some applications might be customer facing, they might have impact on revenue, impact on churn. These applications obviously must have very low latency. Other models might be serving applications that have lower priority, maybe back office applications that are automating some financial transactions, for example, some HR transactions that might get pushed down a little bit in terms of the service level agreement requirements. So the ability to have an inference serving platform that is intelligently able to identify these models and serve them based on their specific SLAs becomes an interesting challenge to solve. Second is interoperability. Now, of course, a lot of AI models today are written with different backends. Some backends could be PyTorch, TensorFlow, Onyx, and a bunch of others. But also some of the models that are in production might have associated pre- and post-processing requirements with them that might not necessarily need to run on accelerated hardware and can potentially run on CPU. So being able to have an inferencing platform serving capability that serves all these different backends, but also serves different hardware accelerators, CPUs, GPUs, etc., becomes an interesting challenge as well. And then on the integration side, this is particularly important when we think about AI, as a lot of enterprises today are carving out significant portions of their budget to invest in AI applications. We're starting to see requirements around making sure that these investments can be easily ported across different deployment models. So some organizations, for example, might be standardized on AWS. We've heard AWS mentioned in a couple of prior presentations. And these organizations might specifically be looking to hire engineers that are certified on AWS SageMaker. So being able to have an inference serving platform that is deeply integrated into SageMaker or Azure ML, Google Vertex AI, et cetera, becomes interesting. But also the ability to quickly port these models and that inference serving platform across different clouds and different deployment models is something that we're hearing come frequently from our conversations with some of the enterprises that we're working with. And then there's a bunch of others. I don't want to drain the slide, but also scalability, efficiency, cost-efficient utilization of the underlying hardware. And of course, the cost to serve these models is a challenge that a lot of organizations are kind of digging a little bit deeper into and trying to find a solution to optimize these particular challenges. Now, zooming out a little bit, at NVIDIA, when we think about inferencing, we think about a full stack solution. And by full stack, I mean, we obviously have at the very bottom the hardware accelerators, the GPUs that are needed to accelerate some of these machine learning models. But also right on top of these GPUs, there are compilers that could help optimize these models to take full benefit and full capability of the underlying GPU. And this, we have a couple of solutions for compilers that we have out there in the open source realm, like TensorRT and TensorRT LLM, that can optimize models to make sure that they're taking full advantage of the underlying GPU. On top of the compilers are the model servers. That's what we're going to be talking about today and double-clicking into that. And these model servers particularly come with features like batching of incoming requests, the ability to serve multiple instances of models, and the ability to do concurrent model execution. We're going to double-click into this a little bit later in the presentation. Now, of course, we also work with enterprises that might not necessarily want to work at that level of the stack and might be looking for higher-level APIs, higher-level SDKs to interact with. And that's where the application frameworks come into play. And here we have a set of solutions as well at NVIDIA that are also open source that offer prepackaged AI use cases around computer vision, around automated speech recognition, and other capabilities that help developers and help enterprise applications, instead of having to build these capabilities at the compiler level and at the model serving level themselves, they can quickly and easily use some of these higher level APIs to deploy applications in production. The MLOps integration, we talked a little bit about this as well. At NVIDIA, we've invested very deeply in our open source solutions to make sure that they're deeply integrated with a lot of the MLOps tools that are out there in the market, SageMaker, Vertex AI, Azure ML, Oracle Data Science, and many others, and offering really one-click deployment capabilities in these machine learning, in these MLOps capabilities and tools. And then lastly, we also offer production and security grade services on top of that end-to-end stack. So for organizations out there that might need 24/7 support, we offer services of that nature. And we also offer security capabilities as well, because a lot of our open source solutions obviously rely on other open source libraries that might have some security vulnerabilities around them. So we offer security grade and production grade branches for our open source software that we make available for our customers as well. So this is what we call at NVIDIA the NVIDIA Inference Platform. It's a full stack solution, and we believe that really solving some of the inference challenges that we talked about in the earlier slide requires a full stack platform to kind of address them. Now, now that we've understood what the full stack looks like, diving a little bit deeper into the NVIDIA Triton Inference Server, quick question to the audience. How many in the room have Amazon Prime or use Amazon Prime? Raise your hands. How many of you that raise your hands also use Amazon Music? Okay, quite a few. So every time somebody searches for a song in Amazon Music, there is an actual semantic indexing model that sits behind that search engine that is served by NVIDIA Triton. So this is just an example of some of the use cases out there for NVIDIA Triton Inference Server. Microsoft Office as well integrates Triton into their product. Oracle uses NVIDIA Triton for serving computer vision models. And just recently, ServiceNow also announced some interesting use cases around the product. We're also seeing a lot of use cases around financial services for fraud detection, American Express, as well as Wealthsimple, in InsurTech as well. So if you can take an image of a car accident and load that image back into an InsurTech application and do some computer vision modeling on it, being served by the NVIDIA Triton Inference Server. In terms of some of the high-level benefits of the product, we've seen organizations report being able to reduce time to market for their AI applications from months to minutes, increase throughput of their hardware as well. So being able to, if you're investing in a GPU or a virtual machine instance powered by a GPU, being able to really maximize that throughput of that machine obviously delivers a lot of TCO for your organization. We've also invested very heavily in interoperability, support multiple machine major frameworks, as I mentioned, TensorFlow, PyTorch, Onyx, etc. We've built integrations with other compilers out there in the market, like VLLM, for example, is a very popular machine learning compiler that we've built integrations with. And as I mentioned, the product itself doesn't only run on NVIDIA GPUs, but also runs on CPUs, allowing you to bundle in some pre and post processing capabilities and have those run on CPUs. And it also runs on AWS Inferencia for those of you that might have models running in the cloud. So I think we talked a little bit about some of these capabilities as well. The fact that the product supports different frameworks, supports different types of models as well. So not just large language models, but there are some applications out there that might rely on tree-based machine learning capabilities like XGBoost, which is very popular in fraud detection and financial services, can also be supported by the product. Real-time batched or audio and video streaming is a capability the engineering team has invested heavily to make sure that the product can also support different query types. And then finally, different hardwares, on-premise, cloud, and different platform types as well. So with that, I want to hand off to my colleague, Ryan, to dive a little bit deeper into the architecture side of the product.
Thanks, Amr. For time's sake, I think I'm just going to give a super high-level overview of the architecture here, and then just show you a really quick start example. So, what is inference serving? What is an inference server? Basically, this is a tool to help you take your machine learning models and deploy them at scale, put them behind some kind of service, right? So if you start over on the right in this model repository, this is kind of the one thing you need to do inference serving. You need a place to have models. This could be a local folder on your server. This could be S3 storage, cloud storage, GCP, anything like that. Triton takes that model, loads it, and then all this magical features starts to happen. So basically you have the lifetime of a request. You have some kind of client library or even just like a curl from the command line. You send a request. We have all sorts of advanced scheduling features, per model queues to optimize the scheduling of the requests, scaling up and down the number of instances per model based on what's popular, what's not. The ability to kind of load these models dynamically, load or unload. Say you have, auto scaling and you have a certain type of service that's more popular, you may want to load more instances of that. All sorts of observability and usability features like OpenTelemetry tracing, Redis caching, Prometheus metrics, and then again, lots of C++ optimized backends for things like TensorFlow, Onyx, TensorRT, etc. So take that all together. Along with the model repository, you get some kind of HTTP or gRPC endpoint that you can query behind your service. So I'm going to skip through a few of these key features that we can talk more at the happy hour if you're interested. But basically, Triton is a completely open source project on GitHub. There's a quick start example that can basically be done in 3 lines of code. All you really need is Docker installed, and optionally the Nvidia container runtime. It also works on CPUs, but GPUs are where it's at currently with all the large models. And this is just an example of that. So I'll probably pass it back to Amr or to our friends from Netflix here for the remainder of the talk.
So just to wrap up very quickly, as we mentioned, the product is available on GitHub, so you can download it from there. But we also maintain our own container repository at NVIDIA. It's called the NVIDIA NGC. You can download it as a Docker container from NVIDIA NGC. And we also have at the very bottom, once you get the slides, I definitely recommend you check that out, the NVIDIA Launchpad. Our Launchpad gives you a very quick, easy access to a lot of the open source products. You can run experiments with them very quickly, and you can get a quick feel of what they can do and some of the capabilities that they can offer. On the right-hand side, for those of you that are interested in some of the enterprise-grade capabilities and services, the 24/7 support, the production-grade, the security branches, and so on, I've included some links for you over there as well. We offer a 90-day free trial, so you can get a feel of what that type of support and services can offer to your particular projects. We've also included some links for any of you that are building projects directly in the cloud and are interested in using Triton integrated as part of SageMaker or some of the other MLOps tools that you might be using. There's tremendous amount of investment, again, that's happened in that space. You can literally implement or download or start running the product with a single line of code on Azure ML or on Vertex AI. So definitely encourage you all to, if you're building your projects directly in the cloud, to have a look at some of these links. A lot of that is tutorial, development how-to guides, etc., that can potentially be helpful for your projects. With that, we do have our colleagues from Netflix that will share a little bit about their own use case for the NVIDIA Triton Inference Server.
Okay, thanks, Amar and Ryan, on the great introduction on Triton. So hi, my name is Fan. I work in the machine learning platform here at Netflix. Today I'll be talking about a service we built called a model scoring service and how we leverage Triton to achieve our model serving need. And my colleague Li Peng will also join me to introduce a little bit more recent work we planned for with Triton to serve our LLM models going forward. So a quick agenda. I will start with a high-level overview of what is modeling service and why we build it. And then I will talk a little bit about how we leverage Triton in the model serving service to achieve model serving performance. And then Li Peng will talk a little bit about how we use Triton to serve LLM models and then our learnings on using the TensorRT backend. Okay, so let's start. Actually, before I jump into the model scoring service architecture, and so just a quick context. The model I'm talking about here is actually our member-facing models. They are not built with the Metaflow. It's actually built with a internal Netflix internal library stack. Is purely JVM based. Anyway, so before I talk anything about model scoring service itself, I think it would be good for me to give you a high level overview of what a typical model serving flow look like in Netflix. So it's actually a very typical flow where you have your model training, you got a model, the model get published to a model registry, and then you have some sort of application that will use the model for any inference need. But one special thing here is that the model we are talking about here is not just the core machine learning model. It's actually a model that contains a full stage of machine learning. It includes the data fetching layer, it includes the feature extraction layer, it influences the machine core ML inference itself, and it also includes other logics we want to apply on top of the inference. So again, this model is actually built with some Netflix internal library. It defines all these different layers, all these different abstractions. So when you build a model, you're actually building an entire thing. The good part about this is that it's a very sort of self-contained battery-included solution. So when you get a model, you don't really need to do any special ceremony. You just use it. The model itself knows how to connect to different Netflix data sources, how to fetch data, do feature generation, and then actually run those models, no matter it's TensorFlow or XGBoost or anything. The other benefits is that since this is a black box with a bunch of standard interfaces, applications can actually use the model and replace it very easily because no code change is needed. You just replace the model, all the interface stays the same. And also for the same model, it can be used by many different apps because it requires nothing. As long as you have the library, you can use it. And it also helps us to achieve online-offline parity because even for offline, when we do the training, it's the same model. It's running the exact same code. But that said, with all the good things, there also comes challenges. One thing is that it runs everything together in the same box, in the same environment. And with the model, with the core machine learning model, TensorFlow or XGBoost getting more and more complicated, it will actually compete resource again with all the other things like data fetching or feature computation in the same box. Sometimes you do want to separate out those machine learning compute itself because those tend to be very heavyweight. That's why we introduced the model scoring service. We want to extract the model inference into a separate service to completely separate them out. So this is the new flow where model scoring service is involved. You still have your training, you have model registry, you register a model into the registry, but now you have an additional step where you can say, for this model, I actually want it to run with the model scoring service. So we have the whole service there to help you do that. We have the front layer where you call this to say, I want to deploy my model. And again, since this model is built with the internal library, we can actually parse the model. We can understand the model. So depending on what the actual model is, we then choose which type of Docker image we want to serve the model with. And we deploy them into our compute platform with all the required resource. At the very last step, after all the deployment is done, we know it's working well, we actually do a repackage of the model. We package it back into the same format. It still have all the different abstractions we have, but if you notice, the inference layer becomes model scoring service inference. This is kind of a transparent change to user. They don't really need to care whether the inference happens on their box or as a separate service. because again, they are coding against the interfaces. They don't even know the model underneath switched the compute platform. So as you can see, one of the Docker image we have is actually Triton backend. So this is where we integrated Triton into the model scoring service. We actually built it as a backend of MSS. While it's sort of can be changed at any time, we have different backend for different purpose. But Triton is kind of our default choice when GPU inference is required. And the good thing about it that is Triton support different type of models. It can serve TensorFlow, or it can even serve XGBoost. It's kind of meet our needs, and it achieved a very good cost efficiency for our main workload. We get several X of improvement in terms of latency and throughput. And also Triton provide a bunch of features or levers where you can tune to achieve even better performance. For example, the dynamic batching, we use it to group some of our traffic together to achieve even better throughput. And there's also a bunch of tools available for debugging and model analysis. So yeah, so this is how we are actually using Triton for our model serving need. Now I'm handing over to Peng to talk about our most recent work to leverage Triton for large language model serving.
Thank you, Fan. It's a great pleasure to meet everyone here. Today, for the next few minutes, I'm going to share an ongoing work with my colleague Lingyi Liu, who is sitting there. And it's about large language model serving with our model scoring service backed by Triton. Our benchmark results last December show that TensorRT LLM has the best serving throughput for our internal use cases. So we have a public talk that's available on YouTube. Due to the time constraint, I'm not going to cover the details, but you can check out the YouTube video to see the exact benchmark results. And TensorRT LLM is the recommended solution by Nvidia to run large language models on Nvidia's GPU. So we decided to adopt Triton's TensorRT LLM backend in our model scoring service. The flow works as follows. After a large language model is fine-tuned, it needs to be compiled into a TensorRT LLM engine. And then a YAML file will be generated during the compilation. Then our model lifecycle management service is going to send a deployment request, which includes parameters like instance type, instance count, and the YAML file location to our model deployment service. The YAML file contains metadata like the engine repository location and the tokenizer repository location. And then our model deployment service is going to deploy model scoring service, which has a GPU Docker. The model loader will first parse the YAML file and get the metadata, and then the engine files and the tokenizer files, as well as the configuration files, will be downloaded so that Triton backend can load. Usually, there are 4 models involved in our LLM model serving. The pre-processing model does the cleaning, tokenization, and the normalization, and prepare the input to the main language model. And then the large language model is a core model responsible for understanding the input and generating natural language text. And then the post-processing model will refine the output to meet specific requirements and improve the quality. This could involve tasks like filtering out irrelevant information, rephrasing sentences for clarity, and adding formatting. And then ensemble model is going to connect the three models together. And our application can talk to model scoring service through HTTP or gRPC clients. And then our proxy will make gRPC requests to Triton backend. Next, I'd like to share some learnings of using Triton to serve large language models. First, although this is not be tested in production yet because it's ongoing work, our benchmark results, as mentioned earlier, shows that TensorRT LLM has great serving throughput. And Triton provides multi-framework support, including TensorFlow, PyTorch, TensorRT LLM, that allows us to have a unified deployment and serving. And we do have some pain points. The first one is Triton image has the TensorRT LLM and required dependencies installed. However, we cannot directly use Triton image because maybe that's the same for other companies as well. At Netflix, we have our own internal base image. So we have to compile TensorRT LLM, maintain all the CUDA and CUDA-related dependencies. This can be a maintenance burden to manage all the dependencies and the environment. And then with enough levers to tune, which offers much flexibility, there are just too many parameters to configure at compile time. This can be overwhelming for users to understand what each parameter means and how they're going to affect the runtime performance. It's challenging to strike a balance between ease of use and optimal performance. And lastly, based on our experience, we found that TensorRT LLM version has to be the same at compile time and runtime. It would be good to have some backward compatibility. For example, after we bump the version at runtime, we don't need to recompile all the models again. Yeah, that's all we want to share, and we're happy to take questions.